Good morning, everyone. Welcome to APCT String Lecture Series. This is the second lecture by Professor Euihun Joung from Joung University. He will continue to teach Coadjoint orbit and dual pair correspondence. Please join me in welcome Euihun.
Okay, thank you. Thank you very much. So I will continue the story about Coadjoint orbits. So yesterday we looked. I told you something about the relevance of Coadjoint orbit in higher spin algebra. Today we move to other applications, which is actually modular particle, and also some representation theory. So just let me remind you that so each Coadjoint orbit and maybe a brief reminder that Coadjoint orbit is that so when you have a Lie group and Lie algebra is generated by this generator, and then a dual space is generated by these dual generators. Then you have natural actions, adjoint action on the Lie algebra space, and then also you can using this duality, you can also define co-adjoint actions on your dual Lie algebra space G star. So then this is a G star space, and any point, any vector, you can act G, and then it will form a surface which form an orbit. So in this way, so this is what is called the Coadjoint orbit. Essentially, it can be also viewed as isomorphic to G mod by stabilizer over phi. Phi is here representative element. So that was the definitions, and then we looked at how this Coadjoint orbit, especially what is called the minimal one, is relevant in higher spin algebra. So today we will see other things. So each Coadjoint orbits are symplectic space. So this is something that we already talked yesterday. Let's see. Yeah, here, Coadjoint orbit is symplectic because vector fields basis of any vectors in Coadjoint space can be obtained by can be generated by this Lie algebra actions on the Coadjoint space. So in this way, any vector field can be just understood as a Lie algebra element here, x and y, and then put two Lie algebra element, and you can define antisymmetric form, which is nothing but the symplectic 2 form. So in this way, you see that we can always define symplectic 2 form in any Coadjoint orbit. So in this way, we can see that Coadjoint orbits are symplectic. So in this way, symplectic is essentially phase space. So we can define word lines. So it's phase space. So we can define some particle actions. Then the third lectures will be the second lecture of today. Actually, we will talk about irreducible representations related by this Coadjoint orbit. This is in a sense, this is what is called the orbit method, essentially. So typically, there is one way to get the representations out of Coadjoint orbit, or out of any actually phase, any symplectic space, is what is called geometric quantizations. This method. But this method can be also applied to Coadjoint orbit. and then we get the quantizations, and then this quantization will give us representations. So this is some sort of conventional thing, but we will not follow this geometric quantization, but still we can see how the quantization can take place. We can do the proper quantizations of this quadrant orbit, which is phase space, classical phase space, and then get some representation which is attached to this quadrant orbits. So this will be the second lecture of today. So the first thing is that we will begin with this worldline particles. Maybe let's put 1 and 2. So this worldline particle. So about that, so essentially what we can do is that this worldline actions, we can immediately write down like this. So phi and then G inverse dg. Here, once again, phi is a specific element in G star, in particular orbit. Certain orbit. Say, yeah. Maybe let me write this Coadjoint, which is again part of G star. So in principle, we can just take any phi of G star, and then that will select that. By that, we select certain orbit in it. And then G is nothing but G is functions of T, which is this here the source manifold is worldline. I mean one-dimensional one. And it's yeah, Lie group valued. And then as we said that actually phi, what is relevant here is that the group element modded by the stabilizer. So in this way, what we can do is that we can always decompose the group element into 2 pieces, where B is belonging to stabilizer of phi. In this way, actually, B simply drops in the computations. So when you do G inverse dg, actually it will become phi and then A dec inverse TA. In the computation, you see that there will be a dB piece, but anyway, so phi do not have any, it's just lying in the other directions, so it's 0.
I have a question.
Yeah.
Here, first one is the really basic question in mathematics. So can you always write the G in terms of this stabilizer on the right action, or is there some like depending on the group, is there some ambiguity on this yeah, I mean, I think it's possible to mode out the stabilize on the right action. Is it, or?
I think so, but I don't know whether there will be any subtlety in doing that. I think it will be possible if there might be possible that AT is not really connected, but if we allow some even such kind of possibility of disconnected AT, I think it will be always possible. Yeah.
And the second one is phi is some fixed element, or
yeah, phi is a constant.
Constant. So like so in this here you have an action. Phi is just a given number. It's not the Lagrangian multiplier or
no,
anything.
it's a constant. Phi is a constant. So here, yeah, it's important that this is constant.
Like a math or
yeah,
okay,
mass or whatever. This is constant.
Okay.
Yeah, so that then it will be actually easier to take example which is a massive scala. So this example actually, so here I present from the point of view Coadjoint actions, Coadjoint orbit, but actually, so this kind of construction has been studied for a long time with the name of nonlinear realizations. So we take this Poincare, and then we can take phi as so here ISO 1 t minus 1 star will be spanned by the dual boost dual translations and dual Lorentz generators. And then here we will take phi, specific phi, so we take just m phi 0. And then what we can do is that clearly we see that it's there is some stabilizer, which is R piece. So R piece is, so this is rotations. Rotation. So this will be boost. So this will be a translation. So we can decompose in this way without any problem. In the case of Poincare, we all know. And the rotation part will simply drop in the computations because it's in the stabilizer of phi. So in the end, what we can do is we compute this object. Then what we get is phi, and then there will be two pieces here. TL inverse, and then DTL. But once again, here the part that where D act on T L will again just simply decouple because when it's phi and then some DL is essentially 0, if you like. LDL, L inverse DL. Phi is only on this translation directions. So in this way, we can see easily that it's effectively T inverse DT and L, only this one. And then what we can do is that we can put phi TL like this, and then T inverse DT. So by putting T as exponential x mu, and then P mu, so what we get is this guy is nothing but T x mu, P mu. And on the other end, L phi L inverse is that we are boosting these guys. We are boosting these guys, and then eventually that we can write down as K mu, K mu, and then P mu, where K square equal M square. So after boosting this vector, we will get arbitrary some directions in the P directions in the P space. So this is such an arbitrary vector, which not arbitrary, but the vector which is given by this boost. And then the condition is that since it starts with the M, so this K square should be M square. Good.
Here I have another question. So here you argue that this phi, there is no DL because the inner product will vanish.
Yes.
So that the reason is phi. You choose the phi, the specific element of phi here.
Yeah. Right. Yeah.
If you choose the other, like I mean, for arbitrary phi, can you always choose it? Go to the sum using the symmetry, you go to this element, or is it just a class of the coadjoint orbit?
So as I will mention later, in fact, this decompositions of G is not. I mean, you can take any decomposition, but depending on how you do it, you get some different expression, which is clearly related to the any other choices. So the point is that you want to decompose in a clever way, in a way that the resulting action has some sort of good manifest covariance. That's the whole point. And then in the Scala case, this is kind of very natural and good things. But if you start to add some momentum PC, the Lorentz part PC here, actually this will become some sort of spinning particles. And in such cases, it will be a bit more subtle to find sort quote unquote natural decompositions. Essentially, this is M, but here M is you can naturally decompose in this way because that's a stabilizer part and all the other part of M.
I have a question. So here the translation means that the special translation, right?
No, all the translations. Yeah.
But for the MP0, I think that the translation along the time is also the stabilizer here.
Right. That's but yeah, that's true. But here I didn't say that. So here, if it's a stabilizer, this will not contribute. But
Yeah.
here I didn't put all the stabilizer here.
I see.
Yeah, just I put part of stabilizer, which is rotation.
Okay, thank you.
To get some covariant action.
Okay.
So in this way, we can eventually get, so this guys is eventually K mu, P mu, and then T X mu, P mu. So clearly what we get will be K mu, T X mu. But here, because we have these conditions, what we can do is that we can just simply solve K0 part, which is plus minus square root K square plus M square. And in this way, we can see that here, K0, Tx0 plus minus, Ki, Txi plus K0 is this plus minus Ki square, and then Tx0. And then eventually by pulling out these guys, x0 is t. So this is t. We just simply get okay, phi g inverse tg is tt times ki and xi dot plus minus square root k plus m square. So this is the usual the Hamiltonian form of the action, where Hamiltonian is like the square root form. So here, sorry, maybe here I should put plus, because actually with the boost we can never generate minus. Yeah, so this is the actions. So indeed we can recover the massive scalar particle actions. Here the remark is the following. So suppose that if we take we want to impose we want to impose this condition as a constraint. That's always possible. So then in such cases it will be like we introduce a Lagrange multiplier E and then K mu square M square. So we know that that's almost equivalent to this. This section is almost equivalent to this one. But the point is that here in this way, by solving the constraint, we get the K0 equal plus minus Ki square plus M square. So there is a two sign. So in this way, we include two orbits actually. Two orbits, phi equal plus minus M P0. So here we cannot include any two orbit because we are beginning with a specific point in an orbit, and then that will simply just pick up one specific orbit. never two. But if we describe, in a sense, the orbit in terms of these constraints, actually it may contain more than one orbit. So this is one remark. And then often we see that more complicated system and some sort of more exotic system, this always, I mean, this kind of subtlety becomes more manifest. The other thing is that remark is a Lagrangian. Lagrangian depends on the parameterizations of G, or if you like, the decompositions of G. So for instance, if I take G as exponential xi, just new parameter, tilde parameter, and vi m0i, and then e minus x0, and then some strange combination that I already took, and then rotation. Then what we get is phi G inverse dg. What we get is immediately some very simple expression where with the change of some relatively simple change of coordinate, change of variable like that, we get the ki dxi. So this remark is that no Hamiltonian. So this is quite natural because any quadrant orbit is symplectic manifold, and symplectic manifold we can always take good coordinate in the sense that if you cleverly choose the coordinate, then symplectic form will be just canonical one. Then in that way, actually, you can always trivialize this everything, and then there is no Hamiltonian, and you can always write in this form the action. This is always in suitable coordinate. You always get this. So from the classical mechanics point of view, this is nothing but actually this clever choice of coordinate, which make this action in this simple form is nothing but this action angle variable. So yeah, so this is essentially Darboux coordinate. Or action angle variable mechanics. And then another comment is that this was the simplest case, but we could extend this to many different cases. Actually, this has been all studied within this nonlinear realization study. Symmetry. That's actually essentially the same. So the idea was the nonlinear realizations is you essentially compute G inverse dg, but there they divide the part of the symmetry, broken, unbroken, etc. According to that kind of scheme, you consider some proper useful decompositions, and eventually you compute G inverse dg, and then somehow pick up one specific component. So essentially, that's precisely this Coadjoint orbit actions, but somehow interpretation was not like that most of the time. But here I just try to emphasize that this can be naturally viewed in this in terms of Coadjoint orbits. So in this ADSD, DSD, whatever. And then, so this is, but even in these cases, most of cases was a scalar particle, because otherwise it was a bit hard to guess, because in a sense, this was based on some sort of nonlinear realization, was based on some sort of guesswork. So it was not easy to understand that by picking up which component would lead which particle. It was not that obvious. But now from Coadjoint orbit perspectives, it's relatively clear that you need to pick up the point phi, pick up the vector phi, which belongs to the orbit corresponding to some spinning particle, if you want to destroy a spinning particle. So more general choices phi in ISO would give good spinning particle descriptions. Moreover, probably even more exotic particles. As in the scalar particle case, it would be important to have a scalar case. Phi G inverse DG just gives good actions, the Lagrangian. Case gives Lagrangian. But without manifest covariance. Yeah. So that's that we have seen already here, right? So if we do just straightforward computations of these Coadjoint actions, we get this expression, which we know that it is eventually covariant, but it's not manifestly covariant. There is some square root and blah blah. However, we know that we can make it manifestly covariant, manifestly Lorentz covariant by introducing some Lagrangian multiplier and rewriting it in this way. So there is some gap here. There is some jump, and which necessarily include some plus minus signs, etc., etc. There is some job to do to make this section, manifest covariant manner. And again, so if we do this for a spinning particle case, again we will get some action which is good, but not manifest covariant. And then this was studied in I think by several people. So people already understood that Coadjoint orbit would give some good particle actions, and then by taking some relatively proper choice of coordinate system, people try to describe this spinning particle. But the limitation was that since it was not completely covariant, manifestly covariant, it was not easy to appreciate the result somehow. So, and then it will be good to have. The question is that whether we can cook up a manifestly. Here, mostly Lorentz covariant description of Coadjoint action. You can ask these questions. Because Coadjoint action already is good, but it's not manifestly covariant. And then, in a sense, this is not that good because depending on how you choose the coordinate system, you may be satisfied or not. It's very strange. It's up to your just the choice of coordinate. If you are too good or too bad in choosing coordinate space, you just end up with just nothing. So you need to properly choose to get this nice system. Otherwise, you would get this. So this is relatively, yeah. So this is the kind of the main point of the game here. So then our aim is that, okay, let us try to invent or just devise some manifestly covariant descriptions of Coadjoint actions. So clearly, we can easily guess that as we have seen in the scalar particle case, we would need some sort of constraint. So we need some constraint system. And then here comes this dual pair correspondence. So let's take the simplest example of this dual pair correspondence. But here classical version.
Before going to the next one, can I ask a question in the
Yes,
previous?
sure.
So in the previous action that you obtained, the first order action, from the point of the path integral, so here, if you consider the path integral, this path integral is integral over x, and because this
Integral over
is
G. Yeah.
G,
Yeah.
K in the result, it seems that we also have integral over the K because it's a conjugate momentum, but it seems to come from the L.
Actually, K is coming from the group, and then P
I see.
is coming from the X is coming from the translation. So both coming from the G. So in the when you put the path integral, probably we need to be a bit careful here because indeed we know that the isometric part simply decouples. So if we completely integrate over G, then we know that there will be redundancy by the the stabilizer part. So probably we need to just divide by the volume of the stabilizer. But anyway, this is yeah, probably that will be related to it. But I don't know precisely.
Thank you.
So let's go to this dual pair correspondence. But for the moment, it is a classical aspect, just as the answer of these questions. So we can take the example like so manifest. We need the manifestly covariant descriptions. Of quadrant orbit actually. It's all about parameterizations of orbit. So it's the manifest covariant descriptions of the action is nothing but the manifest covariant descriptions of quadrant orbit. Manifest covariant parameterizations of quadrant orbit. Let's put here parameterization. Of course. So for that, we can take an example of SO3 star. I could take SO1, 2, which is more physical in a sense, but for simplicity, let us take a more simple but rather unphysical, but still easy to understand example of SO3. So in this case, it's very simple because any orbit is a sphere. So any orbit is a sphere. Phi1, Phi2, Phi3 is just a sphere. Good. So phi is phi I, J I. Since this is a sphere, we can take a parameterization like this. R sine the usual spherical coordinate. R is a constant, while the angle theta and phi, this coordinate is a two-dimensional, which is the good coordinate system for the sphere. However, we know that the theta and phi is not that is not manifest covariant. We don't know how it transforms easily under rotations. So then we have another choice. So maybe let's take this example. So this is first case, and then that, but not covariant. So, and then second choice would be the following. I would like to take phi I in the following way. I, j, k, and q, j, p, k. So this is not very unfamiliar, right? You should be familiar with this kind of descriptions. But in this way, how many? Q1, 2, 3, P1, P2, P3. So we know that this is very, very covariant because we know that the Q is a 3 vector and P is a 3 vector. We can easily act any rotation on it and then it transforms covariantly, linearly, if you like. So this coordinate is very good. It's manifestly covariant, but it's a 6-dimensional. It's completely redundant. Yeah. This is covariant, but redundant. Yeah, so we need to remove 4 degrees of freedom. Because to get 2, you need to remove 4 out of 6. And then in the end, we see that 4 degrees of freedom to remove is actually 2 times 1 plus 2, 1 times 2, in a sense of coordinate, the constraint analysis. So this is a first class constraint. So this is second class. So first class removes twice, and second class constraint is always even number of them, and then removes only 1. And then what is the constraint? Is actually the following conditions. It's QI, PI contraction minus R should be 0, and then PI should be 0, and then QI should be 0. So this is 3 constraint. So this will be the, this is the second class, and this is the first class. It is because if you do the the bracket, then you get actually this one, and this one is R, so it's constant. So it's second class. So remember, R is the radius of the orbit. So we can impose this constraint. And then we can do this. But what is, so yeah, and then, so we can simply impose this 3 constraint on your parameter, which is this one, and this, they are the canonical conjugate to each other, and then we are done. You are effectively describing a particle with a phase, whose phase space is fit sphere in this way. But one can note at this stage is that in fact the constraint is chi1 qi pi, chi2 pi pi, chi3. What appears in constraint, these 3 guys, is actually it forms sp2r. sp2r algebra. More specifically, actually this any chi, which is chi I, ki is sp2 dual space. So it describes an orbit. This is again describes an orbit of sp2r. So as opposed to phi, now I have chi. Phi was something to do with the SO3, while now I naturally get chi, and chi is something to do with the sp2r. So as opposed to this guy is phi I have chi here. So in this way, actually, what we know is that there is this things SO3 star orbits is one-to-one correspondence. SP2 star orbits. So in the end, to recapitulate, so what we get is the actions is simply phi G inverse GG. This action is equivalent to Pi d Qi, and then we impose all these constraints. And then we need to introduce then Lagrangian multiplier. In this case, it happens to be the same line, right? Because it's a special case. Maybe I put here. Then here I put chi I, Q, P, and then I fix some specific number here, which is R00, which is a specific vector Ki. So in this case, so here this is Lagrange. And then Ki is R00. So this will describe the good system. And then actually what we can see is that if you know, I mean, from the Hamiltonian constraint system perspectives, what you do is that to describe the sphere, to describe sphere, which is two-dimensional, you begin with the QP space, which is 6 dimensions, and then you impose the following constraint. You impose this constraint, and then this is a constraint surface, some sort of constraint surface, which is a 3-dimensional. Because we have imposed 3 conditions, and then there is among those there is one first class constraint, which is generating like this gauge orbit gamma. So this is generated by first class constraint. Or gauge orbit. And then you can gauge fix certain things here. So this will be nothing but S2, the phase space, the original phase that you begin. S2 that you begin with. So this is the construction. So we managed to get the manifest covariant things with the example of SO3. But in general, we can do the same game for any orbit of any Lie group. Of course, depending on Lie group, you may have some difficulty, but actually, in most of cases, this is possible. So to summarize, so G star is actually, we can see that we can, what we do is that we describe the space of G star covariant, but redundant parameterization. So what we do using dual pair correspondence, what we do by this one is that we describe an orbit, not only on specific orbit, but actually some part of G star, some part of SO star. In this case is everything actually. all the orbit, all the SO star cases. But in some cases, it's not all the G star, but some part of G star. So in this case, we have an entire G star. So part of G star will be parameterized in this in terms of this redundant coordinate. In this way, we can achieve the manifest covariance, but there clearly will be redundant. So this redundancy can be removed by imposing constraint, but this constraint is something to do with some other group, which is dual group. Is that there comes this dual pair correspondence. So this covariant is that so it means that we have a bilinear in Q and P. So actually, by manifest covariant, what we usually mean is that linear actions. Some vector transform linearly vector. I mean, so in this way, in terms of Hamiltonian form, if the constraint, any actions transformation is made by Poisson brackets, then the generator is quadratic in this canonical variables. Then canonical variables will always transform covariantly. So that's the idea. So in this way, we just realize our G star in a bilinear in Q and P. In this way, we achieve covariance. Then redundancy will be we capture the redundancy, another bilinear, which is describing these redundant directions. Maybe just repeat the same thing times. It's dual redundancy is something to do with the dual group G prime, which was SP2R in the previous example. Yeah. Again, this SP2R was again bilinear of G star. Bilinear descriptions, realizations. So they have quite symmetric form. So maybe to conclude the second lectures, so let me just mention now this way. Actually, what we have now, just changing slightly the perspectives. What we know is that QI, PI is what? So this is just canonical variable that we always use. But this can be also understood as a coordinate system for certain orbit. Which orbit? It's just the SP, symplectic space, because this is nothing but what describes symplectic space. So there is a natural symplectic group. So what we know is that actually this is nothing but a good coordinate system of a quadrant orbit of a symplectic group. But which orbit? It's the minimal orbit. Minimal nilpotent coordinate. In short, we usually say minimal orbit, but here I put all this. So more precisely, we need to mode by G2, but anyway, up to this subtlety, it's just some orbits of SP2 and R when I is running 1 to N. And then what we get is that so all this SP2R is realized as bilinear in Q and P, but among those there are the covariant things, which is G, our space-time symmetry in this example, and there is dual thing, which is also realized as bilinear. Any bilinear is SP2NR. So in this way, what we get is SP2NR just contains both of this group G and G prime. The example of the previous example, we had SO3, and then dual group was SP2R. And then what? We had 3 coordinates, and 6 variable right here. 6 dimensional. So SP6R. sp6r contains both SO3 and sp2r, and they are mutually commuting. So in this way, they are in dual relations. Yeah. So this is mutually commuting reductive group actually. For the correspondence to work, we need to have this reductive group, and then it will be the case is that what will happen is that in the end the nilpotent orbit, this orbit will be simply foliated. This is foliated by the orbit of G times orbit of G prime, and then this foliation, these two guys come in one-to-one correspondence. Maybe this is the good time to stop.
Thank you very much for clear lectures. Please ask any question. If not, we will take a 5-minute break, and then we will start 10, maybe 8-minute break, and we will start the third lecture at 11. Let's thank the speaker Euihun again.
Thank you.
Then we will continue. See you at 11.
Okay.
Thank you.